All right, so the recording has started. So did anyone of you get a chance to go through these questions?
Yes.
So how did you find them? You found them difficult or very easy?
Difficult side पे.
Right, right. All right, so we can begin. Uh, so first of all, our first question is that we have an output y and input x, and both of them are scalars, and they are related by this equation: y is equal to c1x plus c2x square plus c3x cube, which is the standard equation of polynomial regression up to degree 3. And additionally, we have some training data where we have these x5 pairs, and we want to provide the best estimates of what these coefficients or weights in the terminology we may be more familiar with are. So one thing that I did different this time was that I won't be writing down things right now, because I thought that uh, there may be no significant benefit in showing you how I write in real time. So I have prepared these notes beforehand, and we will be going over them. So first of all, what we can do is that we can define our coefficient vector, which is just a stacking of c1, c2, c3. And what we really want is that c1 hat x plus c2 hat x square plus c3 hat x cube is generally close to y. And this subscript I means that we are dealing with the ith example or ith data point. And what this translates to mathematically is that we want to find the optimal, uh, I'll just call it weight vector or coefficient vector, such that this equation holds that c hat transpose into xi minus yi and its norm is generally small, where this xi is just stacking of x square and x cube. And this is something which might be slightly different, but we see that we have really translated our problem into a problem concerning just linear combination, even though there's a square here and a cube here. But we can just use them as separate elements of this vector x. So what would this best estimate entail based on these do observations? Uh, Typically, perhaps also in the exam question, you will be explicitly asked to maybe minimize the L2 norm or L1 norm. Here we can just keep it as an L1 norm, and what this results in it is that we want to that our expression for the coefficient vector turns into something like this. So for each example, our estimate would be C transpose xi, and the actual value would be yi. And we want to minimize the norm between these two uh, scalars initially, and eventually this will translate into minimization of norm between these vectors. And we have just stacked all the examples. So we can see is that this is really the y hat or a predicted y. So y hat 1 minus y1, y hat 2 minus y2. And it can actually be the other way around, since we are doing L2 norm and squaring things. So it doesn't really matter. Additionally, it's important to see what this uh, like opens up into. And a DSP generally, as well as what you will see tomorrow, is a lot about just opening matrices, visualizing them, looking at the interpretations, or maybe matrix multiplication. So we may know, or we can now see that this is equivalent to this matrix multiplication, where I have opened up all the terms for clarity. So we can see that the uh, multiplication of these two, the first element would be c1 x1 plus c2 x1 square plus c3 x1 cube, and so on. So these two expressions are equivalent. And now what we see is that we can write this as a matrix, say, or I have further reduced it initially, because this is also the notation that is commonly used in the notes and otherwise. So for cleanliness, we can translate this expression into this expression, where where x1 transpose really just means this row, and then we can make it into this matrix xc minus y, and this is the standard form which we are familiar with. And in exam or generally all these steps are not necessary, but as part of this tutorial I thought that it may be relevant to show the intermediate steps. And this is a familiar y, ax minus y, and minimization of its L2 norm. We have already seen it. So we know that if x is tall, and what that means is that d is greater than 3, because the dimensions of this matrix x is uh, d cross 3 and c is 3 cross 1, and once again y is d cross 1. So if x is tall, then we'll be getting the least square estimate, which is equivalent to this. Now what I want to stress upon is that this is something we have derived, we have seen the procedure, but what no, first of all I think we can go to second part and then discuss what not to do. So the second part states that how would you estimates update if y is equal to c naught plus c1x plus c2x square plus c3x cube. So this part is the same. What's different is that a c naught has been added and there is no term in x here. So what we can do here is that we can just add a 1 here and perform stacking accordingly, or 1 is equivalent to x power 0. So we just update it like this, that c hat is equal to this vector. The vector x for ith example is updated to this, where the first element is really just 1. And then in our generic notation, nothing changes. So through same procedure as above, the optimal coefficient vector is the pseudo inverse of x times the vector y. So here are some responses, or the type of responses that I have seen in quizzes and homeworks, and this is not like totally acceptable. So one thing is that some of you are very fixated on the ax minus y sort of expression inside here. And although we can like this is just a variable, so I can just say that my matrix A is equivalent to this, and my matrix X, or maybe just C, is equivalent to this term, uh, and then this is Y, and the resulting solution would really be that C hat least squares is equal to A pseudo inverse of Y. But without any definition of what your A is, or what your Y is, or even what your matrix C is. So this is a vector, so there should be like a bar underneath here. So just writing this down, or even just writing this expression down, is not sufficient. When you are asked to show something or derive something, then you really need to actually explicitly state what each of your terms is. So unless it is common knowledge for the scope of this course, at least, for example, we don't define the L2 norm once again, or something of this sort, you need to really explain whatever you are doing. And similarly for part B, just writing something like add C naught term and 1 to the answer is not sufficient. Although we may assume that, although it is reasonably possible that you have reached the correct conclusion and you meant something like this, it is important to write what you really mean. So yes, there's this, and with this we have completed problem 1. Any questions here? I think no, so we can proceed. So here's this second question. We have a full column rank matrix, which means it's a tall matrix with a rank equivalent to n, and then we have a orthogonal projector on range space of A, which we have seen already in homeworks, and otherwise is equal to the product of A and the pseudo inverse of A. And now we want to show that P and I minus P are both symmetric and idempotent. What symmetric means is that the transpose of the matrix is equivalent to the matrix itself, and idempotent means that the square of a matrix is equivalent to the matrix itself. And we have seen that these are some properties of projection operators. So what can be our methodology here? Well, there can be multiple now that you have seen SVD, EVD, and matrix decomposition. So we can resort to that. We can even just deal directly with what these matrices, how these matrices are defined, and progress forward. So there are multiple methods, and especially like in questions where you have to show something or prove something. There are many valid ways, although some methods may be simpler than others. So what I resort to here is using EVD. So we have defined our projection operator P as a pseudo inverse. So since it's since it's a tall matrix, so a pseudo inverse expression is equivalent to this. Then I break down A into U sigma V transpose, and A transpose A is U sigma V transpose, and then the uh, its transpose, which will result in V sigma transpose U transpose. And since U transpose or U is an orthogonal matrix, so U transpose U turns out to be the identity matrix, and so this expression converts to this. Then I have taken A transpose here, then just opened it up once again. Since V so sigma is a diagonal matrix, V is an orthogonal matrix, so its inverse computation isn't challenging, and what we end up with is that our projection operator P is just equivalent to U transpose. And now I have made things easy for me. So by obtaining such an expression, I can just check that, all right, P transpose is equal to UU transpose whole transpose, which is equivalent to UU transpose. Because when we take a transpose here, so it just converts to U transpose, and then U transpose, which is equivalent to this. Then when we do P square, so we just open it up, U transpose U is equal to I, and we end up with UU transpose once again. So we have established symmetry for P and idempotent property for P. Next we move towards,
सर
yes,
कैन यू टेल मी कि आप सेकंड स्टेप से थर्ड पे कैसे गए हो? मतलब आपने जब ये इनवर्स खोला है तो उसको आपने कंप्यूट कैसे की है?
yes,
v सिग्मा स्क्वायर v ट्रांसपोज होल इनवर्स को जब आपने ओपन किया.
right. So जब आप आपका ऑर्थोगोनल मैट्रिक्स है, तो इट्स इनवर्स इज रियली इक्विवेलेंट टू इट्स ट्रांसपोज, राइट?
ठीक है, फिर वो समझ आ गया. ठीक है,
ठीक होगी. And then we move forward to doing the same step for I minus P transpose. And once again, since we have a very easy sort of P, so we take its transpose, it would be I. So when we apply transpose on a summation, we can apply it individually, and we result in the same expression. So symmetry is once again established. So do I need to stress something here? No. Or maybe yes. So UU transpose is not identity. So, this may have been clear, but sometimes people do make this mistake that just the matrix multiplied by the transpose of it when it's orthogonal, they just think that all right, it's identity. But U transpose U is what would result in an identity. Then we go for I minus P whole square. Once again, simple matrix multiplication, and I square is a diagonal matrix with 1, so I square is equal to I, and UU transpose square that is equal to UU transpose. And why is that so? Because UU transpose is equivalent to our projection matrix P, and that is idempotent. So we have already shown that UU transpose square is equal to UU transpose over here. So then we end up with this, and through this expression we once again obtain I minus UU transpose. So this idempotent property is also established for I minus P. So with this we are done, but just although I say a lot that there are multiple ways to approach problems of proof, but never show it, or I do show it sometimes in the homework solutions. So we would also be solving it through another mechanism, which is just using this expression of projection, which is P is equal to A pseudo inverse, and then we can also apply the transpose directly over there. Right. So when we apply transpose here, so once again, since A transpose A is a symmetric matrix, so its inverse won't be affected, and we would result in P transpose is equal to P. Then we do P square. Now this A pseudo inverse, since it's a left inverse, and then we multiply it with A, so this results in I, and P square is equal to P. And then for I minus P transpose, we simply do I transpose minus P transpose, but we have already seen that P transpose is equal to P by the symmetric property of P, and I transpose is a diagonal matrix. So I transpose is equal to I. So we have established symmetry, and similarly by doing I minus P square and using here the idempotent property of P, we can reach that I minus P whole square is equal to I minus P. So this appears simpler and it is equally correct. So but it's just like another method, in another method, whatever you feel simpler. And what we may see later is that something, for example, in the part A, where we have to prove uh, the symmetry and idempotence of the matrices P and I minus P, the second method appears quite simple. But as we move towards part C here, we'll see that SVD and AVD offers us some neat properties which may help us later. So the next question is to show that Py is equal to y and I minus Py is equal to 0. And so we progress towards this. Now, since I have already seen what P is, so I'll just use P as U transpose, then Y is AX. So I have decomposed A into U sigma V transpose, and U transpose U is I. So I end up with U sigma V transpose X, which is equal to Y. Or what we can also do is that using the definition, original definition, that P is equal to A pseudo inverse and Y is equal to AX, we simply reach Py is equal to AX is equal to Y. Additionally, for I minus Py, we can once again just replace P with U transpose and Y with AX is equal to, which is equal to U sigma V transpose X. Multiply these matrices, end up with 0. Or we can also just like open I minus Py, it would be Y minus Py, but we have already seen in the over here that Y is equal to Py. So this would end up becoming 0. Any questions still here?
So if you have a multiplication of two matrices, that you have U transpose and you are taking the inverse of that product, so what will be that equal to?
Uh, so like the inverse of UU transpose,
Yes, whole inverse.
right? So since UU transpose would be symmetric, and we'll have to compute it, because UU transpose is not orthogonal. If it would have been orthogonal, then we could have taken the, then we could have simply done the whole transpose. But in this case, we'll need to compute it, I think.
Okay.
Right. Yes. Yes, Rabia.
फर्स्ट पार्ट के अंदर आपने सिग्मा स्क्वायर्ड का इन्वर्स लिया था, तो सिग्मा स्क्वायर जनरली m by n नहीं होगा?
Sigma square m by n, नहीं, ये हमने अच्छा सही है बल्कि let me see. Sigma. Yes. और ये इट इज एन m by n मैट्रिक्स और फिर हम इसका इनवर्स, यस मतलब इनवर्स तो ऐसे नहीं लिख सकते, बट ये है कि ये चीजें रिड्यूस हो जाएंगी फिर भी, मतलब इसका सूडो इनवर्स आ जाएगा। और
हसन, ये सारी जो इवैल्यूएशन है, दिस इज इक्विवेलेंट टू फुल रैंक एसवीडी, राइट? तो हम उस तरह करके इनवर्स ले सकते हैं।
हाँ मतलब
हाँ
हम
जी, फुल रैंक एसवीडी पे हो जाएगा, सही कह रहे हैं।
हाँ मतलब यू सिग्मा वी ट्रांसपोज हमें एग्जैक्टली लिखने की जरूरत नहीं है, हम ये एस टाइम सिग्मा जहाँ पे हमारे पास जो है वो आ जाएगा, स्क्वायर मैट्रिक्स आ जाएगी, तो उस लिहाज से कर सकते हैं। बट यस, दिस स्टेप एज इट इज स्पेशली जस्ट राइटिंग सिग्मा पावर -2, दैट इज इनकरेक्ट। थैंक यू फॉर पॉइंटिंग आउट। Right, so now we have to show that the range space of A is equal to range space of P. And here things get a bit interesting. So as we have seen in previous tutorial and otherwise, to show the exact equality, we need to, if we are going in a step-by-step manner, first we can show that range space of A is a subspace of range space of P, and then show that the reverse relation also holds that range space of P is a subspace of range space of A, and these two things can only be valid when range space of A is equal to range space of P. So here we leverage the wonders of SPD, and so range space of A is equal to range space of U sigma V transpose. Then I just multiply identity with this. So range space of U sigma V transpose V sigma transpose U transpose U sigma V transpose. And how I came up with this is, or maybe I can just go to next step and then it would become more clear. So this is something interesting, that this space is a subspace of this space, and what I simply do is that remove these three terms, and we can just add any more number of matrices here equivalent to identity and can break anywhere from the right, because what is happening is that this is a more general sort of space, and then we restrict it through some particular linear operation, which is a matrix multiplication. So this holds. And what I'm looking for is that I want to say that range space of A is a subspace of range space of UU transpose. And at this point, what I just wondered was that if I can like change this expression to UU transpose, then I should be good to go. So I just multiplied it with an identity. Then I observed that this is the subspace of U sigma V transpose V sigma transpose U transpose, and through this this is once again V transpose V is an identity, sigma sigma transpose is an identity. Yes, and what I'm left with is range space of UU transpose, which is range space of P. So I've established the range space of A is a subspace of range space of P. Then I go the other way around. Here I have UU transpose, but what I want is U sigma V transpose. So if I can do something to get sigma and V transpose further ahead, then I should be good to go. But I cannot just like write R U transpose U sigma V transpose and stop here, because here I am multiplying it with another matrix. But what I can do is that this expression is equivalent if whatever follows from here is the identity matrix. So I change this expression to this expression, and then I note that this is just a subspace of this thing, and U transpose U is identity. So I am left with range space of U sigma V transpose, which is equal to range space of A. And through this, I have established that range space of P is a subspace of range space of A, resulting in this final conclusion that range space of A is equal to range space of P. Any questions here? Right. So we can, so this is how we leverage the decomposition of a matrix to really simplify proof in a few lines. And we can also see in,
Listen,
yes,
could you repeat how you established that the expression above would be the subset of the expression below?
yes.
Because it seems like a lot of
So this,
acrobatics.
yes. So this expression in itself is, so the range space of this matrix is a subspace of range space of this matrix. So we are dealing with spaces, and what I'm saying is that already this is a more general space, and through some by doing some particular matrix multiplication, I am restricting the values it can take in an intuitive sense. So this is the main expression. Then I multiply everything that is in here through some particular values, and through this space becomes a more or the vectors in this space are particular variants from here. Does that make sense or not?
कि थोड़ी generality डाल रहे हैं इस तरह का सोचा था
हाँ, मतलब अगर हम इसे जो है थोड़ा सा कन्वर्ट कर लें इन दी सेंस कि यहाँ पे हम ब्रेक कर रहे हैं।
मुहसिन इसका प्रूफ हमने लेक्चर में भी किया हुआ है, जहाँ पे हमने प्रूफ किया था ना कि ए मैट्रिक्स कैन हैव ओनली लेफ्ट इनवर्स और राइट इनवर्स बट कैन नॉट बोथ। तो वहाँ पे हमने प्रूव किया था कि इफ देयर आर टू मैट्रिसेस ए एंड बी एंड इफ यू मल्टीप्लाई ए विद बी देन रेंज स्पेस ऑफ ए, ठीक है, तो वो जो है उसका सबसेट होगा। ये नोट्स में भी है इसका प्रूफ।
यस,
राइट, आई रिमेंबर नाउ।
मतलब मैं भी ये करने लगा था, लेकिन एग्जैक्टली यही कि अगर हम दो मैट्रिसेस में देख लें तो इट माइट बी बेटर टू सी। लेट मी जस्ट इरेज दिस। Right. So we can also view this through another method, which is, once again, since we are following that earlier convention of using P directly. So first what we show is that P times A is equal to A, and we can prove it through this multiplication, or additionally, so if you are using it as part of the argument down the lane, we know that the P is a projection operator, and we obtain this, and then we also note that 1 minus P times A is equal to 0. So once again, this is something you get when you get comfortable with these types of problems. So what our argument is that once again, we follow the same procedure at a higher level of showing that one space is a subspace of other, then showing the reverse of it, and then completing the proof. So we take a element from the range space of P. So y is equal to px by definition of range space, which is equal to a pseudo inverse times x for some x. And if we change this a pseudo inverse times x into another variable v, so y is equal to av. And this is, so here it is, we can also like write it as x2 or x prime. So this expression is a valid expression if y is from the range space of A. So through this equivalence, we say that y is an element of range space of A, and we have derived this expression that range space of P is a subspace of range space of A. And next, what we do is to show that range space of A is a subspace of range space of P. We say that range space of A is equal to range space of PA, because both of these two things are equivalent. And then using the same argument as earlier, that range space of AB is a subspace of range space of A. So range space of PA is a subspace of range space of P. And through this we reach range space of A is equal to range space of P. So these type of proof can take some, not exactly practice, but experience to like really note down these equivalences and stuff like this. But if you have this higher picture in mind, that I have to maybe just show these two equivalences, then you can probably approach it in even more ways. So this brings us to the last part of this question, which is showing that x, the inner product xy defined as x transpose A transpose into AY is a valid inner product. And what we do here is just see what the rules of a valid inner product are, what the axioms are, and if all of them are satisfied, then we can call this a valid inner product function. So what are those rules? So first is that the inner product of y and x should be equivalent to the inner product of x and y. The second rule is that inner product of alpha x and y should be equal to alpha times the inner product of xy. And third rule is x plus y and z's inner product is equivalent to the sum of inner products of xz plus yz. And last is that the inner product of a vector with itself should be greater than 0. And now once again, this is just matrix manipulation. And while in some questions like question 1, you should be comfortable in uh, visualizing how they are in an extended or most open form. Here you should be comfortable dealing with it in a more compact notion. So I just use the definition of whatever my inner product is here. So it would be y transpose AX. And I want to show that this is equivalent to x transpose A transpose A times y. So I see that, all right, I can do a whole transpose here, and this is equivalent to AX transpose times AY. We can see that it's really the expression of a dot product, or we can like maybe open it up and visualize it that way. But since it is equivalent, so I just use AX transpose AY, ending up with this expression. So my first property is satisfied. So for the second property, I note that the alpha is just a scalar, so we don't need a transpose here. And what remains is really the dot product of x, the inner product of x and y, and this is also satisfied. Next, once again, we replace this x here with x plus y z. Then we should see that this would be like x transpose plus y transpose, and then we'll x transpose times this expression plus y transpose times this expression. So we end up with this, and this is really the inner product of xz plus inner product of yz. So the third property is also satisfied. The fourth property, which is the inner product with self, so just putting in the definition, then seeing that this is equivalent to AX transpose times AX. And since this is the dot product of AX, and we know that the dot product is a valid inner product. So this follows from knowing some other thing. Although like I have not explicitly mentioned it, but maybe mentioning it would have been better, that I am using this notion that dot product is a valid inner product. So the self dot product of AX should be greater than 0. And uh, through this rule, I have obtained this. I have deduced that x and x in a product is greater than 0. Since all conditions hold, so xy is a valid in a product function. Right. So next problem is where we have to show that this function is convex. So I intentionally made x a function of 4 other scalars or 4 other elements, so that hopefully none of you tried opening it up and resorting to the fundamentals of Jensen's inequality and proving it, because this can get very, very hard, right? So what we should really look at doing is trying to figure out some properties that we can leverage, and some of the properties you have already seen, others uh, you may know of, or maybe through some patterns that you see emerging here. So what are the patterns I see is that, all right, this is a summation of 2 terms, and in the homebooks I have seen that the summation of 2 functions where the functions are convex results in another convex function. So like I can just say that f of x is equal to f1 of x plus 5 times f2 of x, and if f1 and f2 are convex, then f of x would also be convex. So if so there is this one pattern that I see, and if I can show that f1 and f2 are convex, then I'm good to go. But f1 is still a fairly complex function. If I had maybe just let me call this whole thing z1, where z1 is once again another scalar. So if z1 power 4, if I can show that z1 power 4 is convex, that I can probably do. Similarly, if I can show that e power z2 is convex, that may also be something I can do. But then what remains is that showing that I can replace this whole thing with z1, or I can replace z1 with this whole expression, and the convexity still holds. And here I will so this is something I need to prove. So here is just a comment that you see that it's quite difficult, and although it won't, something like this wasn't even asked in the homeworks, but in exam it would definitely not be the case that we ask you to open this up and prove convexity. So resorting to the fundamentals, and like it would probably be unnecessarily wasting your time. So I've already discussed that. So this is once again the outline. So we will use the property that f of x is equal to f1x plus f2x. So I think in the homework these weights for 1, but this generally holds for any non-negative weights, and even in the homework solution, if you can go back and see. So we did not do much with the weights, and the argument just hold on w1 and w2 being greater than 0. Next is this, that we can show that if g of x is equal to f of ax plus b, and f of x is convex, then this g of x is also convex. And here I want to stress, because I saw this issue in some homework, that in tutorial, when we discuss some property, you often use it as a kind of sufficient condition that, all right, any function here, if I replace it with any function here, then g of x would be convex. Or like maybe by in some of the proofs in homework or otherwise, what I really show is that since some property does not hold, therefore we cannot therefore we can show that it is valid, but that is a sufficient condition. But if some property which is sufficient does not hold, it does not mean that we have disproved it. So we have to be clear about what's necessary and what's sufficient. And here the stress is that for particular types of transformation, so I am transforming, like instead of f of x, I am transforming x through ax plus b, which is what we call an affine or affine mapping, which means that the expression here is a linear combination, but more specifically that the resultant mapping, or the points after uh, undergoing this transformation, are collinear. So if they lie initially on the same line, after the transformation, it would lie on the same line. But if you're not very familiar with it, you can take it really to be a linear transformation. Right. And the last thing is that we show that this F1 and F2 are convex. Let's begin. So this is something which is like ideal if you like even write stuff like this just to be clear. So what is F? So F maps from N to R, N to R, G maps from R, M to R. So this B is n dimensional vector, X and Y are m dimensional vectors. So it helps you see if your argument is correct, because a lot of times you can simply see that you are going wrong by checking the dimensions, because this is something that has been frequently encountered in the graded components. Even when I was taking the course, that you do mess up the dimensions and you do like algebraic manipulations which are not even valid. Anyway, so now I'm resorting to the fundamental Jensen's inequality. So g of lambda x plus 1 minus lambda y is equal to f of, since g of x is equal to f of ax plus b, right? So Tahir, are you still here?
Yes.
Sir, I think I'm really low on battery, so I'll share these notes with you. And if I disconnect, then maybe
Okay.
you can like continue from here.
Okay. Okay. Yes.
Let me just share the notes. Right. Let me reshare my screen. Right. So, in fact, I think yes, the light has come, so it won't be an issue, hopefully. No. Right. So, since g of x is equal to f of ax plus b, so we just replace this term and put it inside, like f of, instead of ax, we write this expression, and then a times lambda x. Lambda is really a scalar, and additionally, we should actually be dealing with lambda I, but with scalars we often like neglect this equation or this specificity. So this converts to f of lambda ax plus 1 minus lambda ay plus uh, lambda b plus 1 minus lambda b, where no, this is something, right? So then we convert it to uh, just by or reorganizing it. So it convert. So how we got this lambda b, and this is that we just added plus lambda b and then subtracted lambda b. And these are the kinds of trick that you start developing after maybe you have done a couple of proofs. So uh, here, by adding lambda b and subtracting lambda b, what I know is that I want an expression like this. So with the final outcome in mind, I made this transformation, and this is something you will see extensively in proofs that we add, that we multiply it with one or identity, or we add or subtract something. So through this update, we end up being, by further reorganization, it is equal to f of lambda ax plus b plus 1 minus lambda ay plus b. And using the information that f is convex, we can say that this is less than lambda f of ax plus b plus 1 minus lambda f of ay plus b. which is equal to lambda gx plus 1 minus lambda gy. And so through this we have really proved that g of lambda x plus 1 minus lambda y is less than equal to lambda g of x plus 1 minus lambda g of y. And through this we have actually shown that if f is convex and g of x is equal to f of ax plus b, then g is also convex. Now what remains is showing that the two functions x power 4 and e power x are convex functions. For x power 4, once again we use the Jensen's inequality, and we show that lambda x plus 1 minus y 1 minus lambda y, so this function power 4, and then what we do is that we break it into two squares. So this expression square, and then we use the once again property that x square is convex. And this is something we do not prove, because maybe through the most fundamental visualizations we visualize the function x square, and it is a typical example of convex function, so I do not prove that. But through this notion I know that this is less than equal to lambda x square plus 1 minus lambda y square whole square. And then once again this is like another square, so I can I see that this is another function in the form of x square, and I reuse the Jensen inequality, and I end up with this expression. And once again this is something you should be like consistent with. So if I am just reorganizing this expression, there should have been an equal to here. If I continue writing less than equal to, so this would really mean that this expression is less than this, or which is here it is the case, but next it isn't the case. So you need to like keep these small things in mind as well. And through this I see that like x lambda, this expression is less than equal to this expression, and this is really lambda f1 of x plus 1 minus lambda f1 of y. So I have also shown that x power 4 is a convex function. Next I want to show that e power x is convex, and here I use a property, and the property is that if second derivative of a function is positive at all points, then the function is strictly convex. And strictly convex just means that this inequality is simply less than and not less than equal to. So this is a property which is often utilized in the for proving convexity of simple expressions. But here once again I stress that the converse is not true. So it isn't like you come up with a, or you get an expression in exam and the second derivative is not positive at all points and you say that it is not convex. So this does not hold. So this is once again what we call a sufficient property, that if this is true, we can be certain that the function is convex. If this is not true, then it may be convex, it may not be convex. Something different is a necessary condition. If the necessary condition is not true, then we can be sure that so if I have some condition which is a necessary condition for convexity, so if that does not hold, I can be sure that the function is not convex. And what is a necessary condition for convexity? That is the Jensen's inequality. That is one. All right. So we have like derived all the intermediate results. We have seen an overall map, and here we just like connect them all. So f of x, we started with this expression. Then I say that all right, this is equal to z1 power 4 plus 5 times e to the power z2. And then I say that this is equal to f1 of z1 plus 5 f2 of z2. And since these two functions are convex and there's the summation and here is a positive weight, so this whole expression is also convex, and through this I have proved the convexity. Any questions here? Right, so we can move ahead then. So this is a very simple problem. You just have to do some just follow some steps, and there would be some questions like these in exam. There were even in homeworks, not perhaps in quizzes, where we just like test if what you have studied in class you have really gotten hold of the uh, understanding and the steps involved. So like this is f of x, and this maps to this expression, and we have been asked to compute the gradient and the Hessian of this function. So what is a gradient? Since it's a function of or x is an element of R3, so we can break this down into, or we can just open it up. So this is equivalent to this expression where we take the partial derivative with respect to x1, then the partial derivative with respect to x2, and the partial derivative with respect to x3. So how do we take partial derivative with respect to x1? So all other x2, x3 are treated as constants. So this term would go away, this term would go away. The derivative of this term is simply 6x1. The derivative of this term, so 5 and x2 are constant, so this is plus 5x2, and here x2 and x3 square are constant, so x1 would go away, plus 3x2 x3 square. And similarly, we'll take the partial derivative with respect to x2 and partial derivative with respect to x3. And we are done with the gradient. For Hessian, this is the expression where I like write f with the subscript x2, x1. So this is like partial derivative of f of x with respect to x2 and x1. So this is a slightly neater notation. And in things like this, we need to save time. And what we know is that Hessian is a symmetric matrix. So if we compute either these 6 terms or these lower 6 terms, we can really find everything. So there's this slight caveat that Hessian is symmetric when the double derivative is continuous, but I don't think you will be encountering uh, like functions where the double derivative won't be continuous. So you can take just Hessian is symmetric and we compute the particular term. So once again, you already know that what fx1 is and what fx2 is and what fx3 is. So you use these results from here, and once again this is like, and possibly a simpler partial derivative. So we have only one term in x1, others are constant, they go away, we are only left with 6x1 terms, 6x1 term, and the partial derivative of it is 6. And we repeat the same procedure for the other terms. We compute the 6 terms and then we combine them. And the remaining portion was that, can you compute the stationary points based on this information alone? Well, this is something we have also seen in class. And how do we do it? We like equate these individual expressions and we equate them to 0, and then we uh, like find what the values of like x1, x2 and x3 here, or x1 and x2 in a 2 variable function may be, and we find the stationary points. And the next step is to find if those stationary points are saddle point or minima or maxima, but that is something you have already seen. And these are the type of things that I'd suggest you practice on, since it's expected that these types of straightforward questions would pop up in the exam. Question like this, or maybe a question like simply computing the projection of range space or computing the null space. So these are like free marks and you should be well prepared for it. Any questions here? Right. So this brings us to our last problem. So we have a very simple function that f of x is equal to a transpose times ax minus y. Once again, for a proper definition of this, even this question, I should have mentioned that a is an element of Rm cross n and x is an element of Rm and so on, but I like resorted to some time saving, or I don't know. Right. So the question is that I want to express f of x in terms of bx, where b is a matrix and x is something already known. So here it just means that I have to do some matrix manipulation. So I open this expression f of x, then I see that it is A transpose AX minus A transpose Y. But what I want is that I want something, so I want an X, the vector X here. So how I can bring it here? So once again, I'll use the property that if I have a 1 here, then things would be really easy for me. So what I do is that I just multiply and divide it with the L2 norm square, so X transpose X and X transpose X. Then I combine this expression here. So this is X transpose Y X square and this X is outside. And now I see that I can just like factorize it or simplify it to this expression. And if I call this whole thing as B, so I have ended up with f of x is equal to bx. And what would the gradient of this be? Well, I have already seen that if f of x is equal to bx, or we have seen like more complex things in the homework where maybe it is x transpose ax and stuff like that. So the gradient of it is b. So any questions here? And you can simply ask questions. Raising hand isn't necessary, right? Yes, Mohsin.
Something that really throws me off is that X transpose within the definition of B. So wouldn't that affect our gradient?
Right. So does anyone else think the same? Right, Mohsin. Well, this is a good observation, and this is something that we wanted to come to. So sometimes in matrix manipulation, you will go too deep into it that you will forget that where you came from. And these are the type of careless mistakes that you end up making. And here it is important to realize, as Mohsen mentioned, that B is a function of X itself. So while in our reduction procedure, if we come up with some complex terms and we just reduce it into uh, other variables or matrices, we sometimes forget our foundations. So B really is a function of X. So we need to take the derivative of B as well if we are like using this expression. Or what we can do is that we started off with a very simple expression. So for the gradient of f of x, we can just resort to the basic expression. The two requirements of the question was to find the gradient of f of x and represent f of x in terms of bx. So we have done this. For the gradient computation, I can just use this directly. So this is independent of x, and this is dependent on x. So if I use like A transpose A is equal to B here, so I know that the derivative of that is b. So the gradient of f of x is A transpose A. And this is something that I wanted to stress, because in some questions the terms do become messy, but it is important to uh, note that we shouldn't be put off by these complex expressions or forget that while things appear very neat, they may sometimes be more complex and require more thought. So with this, I conclude